Hello there, and in this video we're going to do another example on how to compare the differences between two population means. So let us consider the following example. Suppose you live in a place such that there are two different routes to work, one through the city and one through the residential district, as shown in this picture above. You measure your travel times on various days and obtain the following results in minutes, namely 52, 71, 72, 52, 71, let's see if I got the data right. Yeah, that's right. 77, 73, 65, 68, 82, 54, and 58, 62, 54, 85, 73, 49, 42. So let us assume that we want to sort of see which route is better on average for any particular day, like which one is the quickest way to go. Even though Route A may appear to be the shortest way, Route B may be the quickest way depending on, traffic, flow, and construction work and so on. All right, so let us pose our question of interest. Is there a significant difference in one route over the other? And we're going to assume that variance A does not equal to variance B due to A being a business route and B being a residential route. So it's safe to assume that the variation between these two routes is going to be completely different. All right, so based on our samples, let's calculate all of our statistics. For example, our sample mean, our sample variance, sample size, degrees of freedom, and so on. So if you want to take a couple minutes to sort of get this information in Excel and do some analysis, please take the time to do so. You should get that the mean of Route A is going to be 67.2 minutes. The sample mean for B is going to be equal to 60.3 approximate minutes. So from these two things, you should be able to see that XD, or the difference between these two means, so let's define XD to be equal to XA minus XB. This is going to be equal to 6.87. So we're going to use this as a point estimate for mu D. Same as before. All right, so also we can calculate our variances for A and our variances for sample B to be equal to 97.96 and 264.67. So even if we didn't make the assumption that the variances are unequal, based on these sample variances, we may be able to even have the evidence from an F-test to support that. Also, our sample size for A, our sample size for B is equal to 10 and 6 respectively. So from these two things, we can get the degrees of freedom for A and the degrees of freedom for B are equal to 9 and 5 respectively. All right, so these are our main statistics that we're going to use in this test. All right, so just a quick bit of theory here. So since we're testing mu D, and since we know that sigma A squared does not equal to sigma B squared, this is where we're going to use a Welch's unpooled variance t-test. Remember that if the variances are equal, we can pull the variances together. If the samples are dependent, we can use a pair difference t-test. But neither of those are true. Since these samples are independent and the variances of the populations are unequal, we use an unpooled variance t-test to perform. So the Welch's unpooled t-test is very straightforward. The only real complicated part is calculating the degrees of freedom for the hypothesis test. So the degrees of freedom for the hypothesis test for a Welch's unpooled variance t-test is going to be equal to SA squared divided by the sample size of A plus the variance of B divided by the sample size of B, the quantity squared, all divided by the variance squared, or the standard deviation to the fourth, divided by the sample size squared times the degrees of freedom for A, all on the bottom, plus the same exact thing except replace A with B. So we're going to have SB to the fourth divided by NA to the second times the degrees of freedom. So this is the degrees of freedom for Welch's unpooled variance t-test. So if we plug in all our values, we're going to get that this is approximately equal to. So for the top, we're going to do 97.96 over 10 plus, so let's write that out. So 97.96 divided by 10 plus 264.67 divided by 6, the quantity squared, all over 97.96, the quantity squared, because this is already squared in here, and 2 times 2 is 4, all over the sample size, A, which is 10, squared times the degrees of freedom, which is 9, plus 264.67, the quantity squared, all over 6 squared times 5. So if you do this correctly, you should get, let's see, 2,905.93 up top, divided by 711.15, approximately. And then once you divide that out, you're going to get the degrees of freedom is approximately equal to 4.08. Now, some people round the degrees of freedom to the nearest whole number, either up or down. It really depends on preference. So you may see some people round this to 4. Some people may even round it to 5. But usually, I don't know. Let's just round it to 4. But some people just use this strictly as the approximate for the degrees of freedom, and which is what we'll do. So if you calculate your degrees of freedom, then you can calculate your critical value. But before we calculate our critical value, let us formally state what our null hypothesis is. So our null hypothesis is that mu d is equal to 0, and our alternative, we'll choose the two-sided complementary alternative, which is of course a two-sided alternative. So if we choose a two-sided alternative, that means of course we'll choose a two-sided critical value, which is T alpha over 2. So this is going to be equal to T.IMV of 1 plus C over 2. So let's operate under a level. What kind of confidence region do we want to work under? Let's work under 0.92. So that's going to be 0.08. So this is going to be 1 plus 0.92 divided by 2, comma, our degrees of freedom. We'll use the exact value of 0.8, 4.08. So that's going to give us a critical value of approximately equal to 2.3329. All right, great. So once you calculate your critical value, then we can calculate our pooled or our Welch's marginal error. So our Welch's t-test marginal error is going to be T alpha over 2 times the square root of SA squared divided by NA plus SB squared divided by NB. And remember the difference between this one and the pooled variance t-test? Here, for the pooled variance t-test, those were equal to SP squared, both of them. That is, we bring them together into 1. But since the variances are unequal for the populations by assumption, we need to treat these entities as separate variances. So that's pretty much why this formula exists in this way. So if that is the case, we're going to plug in all our values. So 2.3329 times the square root of the variance of our first sample, which was 97.96, divided by our sample size of A, plus the variance of the second, 267.67, divided by its corresponding sample size, which was 6. And once you calculate that out, our marginal error is going to be approximately equal to 17.13. All right, wonderful. So once we have this, what do we do? So if we have our marginal error, our confidence interval for our mean difference under a 2% confidence level. So as a point estimate, we're going to use x bar d, and then we're going to subtract and add our marginal error to that. So once we do that, what do we get? So recall our point estimate x bar d was 6.87. So we're going to subtract 17.13, and then we're going to add 17.13 to that, and that's going to give us our confidence interval for the population mean difference. So this is going to come out to negative 0.4 approximately and 24.0 approximately. So this is our confidence interval for the population mean difference. So now we can analyze. So our null hypothesis was that mu d was equal to 0. And 0 is within this confidence interval. You may want to argue that 0 is really close to this left boundary, but nonetheless it is in between. So therefore, since mu d lies within our confidence interval, that means what? That means our sample sort of agrees with the null hypothesis. Barely, because it's really close to this left hand, but nonetheless it does agree with it to some degree. So since this is true, then that means we're going to fail to reject the null hypothesis that mu a equals mu b. So in terms of the application, what does that mean? That means based on our study, there is no significant difference in the travel times among the two routes. And that is our conclusion for a hypothesis test. So to pretty much quickly outline how to test the population mean difference. So the first thing you need to ask yourself is, are your samples independent or dependent? So if they are dependent, then you're going to use a paired difference t-test. And if they are independent, if your variances, sigma a squared and sigma b squared, are equal, then you're going to use a pooled variance t-test. And if the variances are not equal to each other, then you're going to use a Welch's unpooled variance t-test. And remember, you can sort of test the equality of variances with an f-test if you want, if this is not given to you. But this is pretty much an outline of your 3 different hypothesis test strategies for testing for the population mean difference.